Swayam Prabha. Digital India. Educated India.
Hello dear friends, welcome to this fifth lecture of Module 5 on Engineering Geology of Dams and Forces Acting on Dams. In our previous discussions, we have discussed about different types of dams and a brief about the concept of forces acting on dams. In present lectures, we will learn the details about different types of forces affecting the stability of dam by considering an example of gravity dam, because gravity dam is an ideal and engineered dam. In addition to this, we will also summarize about engineering geological characteristics for dam construction. In this lecture, we are going to elaborate about forces acting on dam and geological consideration related to characteristics for dam construction. In this lecture, we are going to elaborate about the forces acting on dam, particularly external and internal forces, and geological characterization for dam construction. Friends, the forces acting on dam can be divided in two categories: internal force and external force. Internal force, we are having, you can see here, the pores. If the water present in pores and the water present in pores is the resulting pore pressure, and that we are going to utilize during the stability analysis of dam as a internal force. We are here considering the maximum external force due to impoundment of the water, due to weight of the water, due to weight of the structure. In this way, we are going to classify major external forces as gravitational forces or weight of this structure, then the hydrostatic force due to impoundment of water, both vertical and horizontal, present in headwater region and tailwater region, then hydrodynamic force during the earthquake and others, during vibrational effect, then the upthrust acting force due to filtration of water inside this foundation, then wave force, then silt force, seismic force and ice force. This we have already summarized. In external force, caused by the weight, caused by the water, caused by the surrounding effect. In water, we are having three divisions: hydrostatic acting headward side and the tail side, then the upthrust due to filtration, hydrodynamic during the earthquake or vibrational effect. This hydrostatic force in headwater region, hydrostatic tailwater region, this force vertical can be divided vertical and horizontal, in tailwater region also vertical and horizontal. Gravitational force or body force, it is simply calculation of this force weight, that is simply unit weight of concrete multiplied by volume of this structure in unit weight. So here we are considering this length is 1, so we are going to calculate. So this type of structures, you can calculate this here area, here this area, and multiplied by unit weight per unit. This area triangular can be easily calculated. In case of the water pressure, you can see here the water pressure present in this type of situation and present in this type of situation. This water present here is going to produce, as we have already discussed, three type of pressure: hydrostatic, vertical and horizontal. Vertical in this case is not going to affect the dam site. In this case, this vertical is a simply area, this area plus this area multiplied by unit weight. So hydrostatic vertical is equal to this area plus this area. Area 1, area 2 multiplied by unit weight of water can be easily calculated. In case of this, there is no vertical. So in certain situation it may be vertical, it may be not vertical. In this region, if we are going to see a horizontal force, as per concept you know well, this forces acting at here 0 and maximum. So this triangular diagram is representing hydrostatic horizontal force located in headwater region, that is simply half unit weight of water into this head H square. Similarly, in tailwater region, the same concept, hydrostatic tailwater, vertical and horizontal. Vertical we are getting here this vertical column water, in this also vertical column water. This vertical simply this calculation of this triangular, and the horizontal simply half unit weight of water then H dash square. The resultant horizontal force due to hydrostatic, due to position acting at the 1/3 into H, that is depth of water from the heel of, from this bottom. In this also, this acting at towards the downwards going to push this dam. However, the same concept acting at 1/3 H dash toward the upstream going to support the stability of dam. In addition to this, we have upthrust due to percolation of water. Here you can see upthrust. The water present here percolate through this, going to create pressure, that is the upthrust. If this the depth of this water H dash, here H, this H dash is 0, then the pressure diagram or force diagram is like this. If this is the B, if it is H dash considerable, then the pressure diagram is like this or force diagram is like this. Then we can easily calculate the head developed due to presence of water at the headwater region and at the tailwater region. This is the H dash, this is the H. Simply this area we are going to calculate. If this is the B, then we can easily calculate upthrust. Upthrust is the unit weight of water multiplied by width of the dam into this here area of this H dash, rest is H minus H dash. So this triangular area, that is the half H minus H dash into B plus this whole area B into H dash and whole multiplied by unit weight of water. Simply we can recognize here unit weight of water into B plus H dash plus half H minus H dash. It simply, you can see, half unit weight of water into B, then this half H and minus this half H, so half H plus half H dash. To reduce this, if we are going to create one opening here, then this pressure or force is going to reduce by this. So only this level of pressure is going to work up, and this resultant is acting at B by 3. B by 3 from this heel point. So resultant is acting in case of the upthrust. Therefore, we are going to create gallery to reduce the pressure build up due to seepage of water inside this dam. Next type of force is a wave pressure. Friends, you all know that the water, if going to interact with wind, then there is a generation of waves, and this waves is going to flow where this upper portion is a 2 by 3 times wave, height of wave, and the wave portion present below this water is 1 by 3 H wave. Due to this movement, the water wave is interacting here and going to create thrust P0. This P0 is acting at HW by 8 from the surface, and this effective zone is the area of this multiplied by unit weight of water, affecting 5 by 3 HW. Then the force due to wave we can calculate simply by lot of formulation at 2.4 unit weight of water, then height of wave, and this height of wave 8 at HW by 8 above the still water, where this height of wave can be recognized if the fence distance is less than 32, then it can be calculated with help of fence distance and the velocity of wave 0.032 under root V into F plus 0.763 plus 0.271 F power 3 by 4 for fence distance less than 32 km. In case of the more than 32 km, the height of wave can be determined simply 0.032 under root B into F, and in this way we are going to calculate height of wave. The total force due to wave action can be recognized as half 0.5 into 2.4 unit weight of water and the height of wave multiplied by 5 times height of wave divided by 3, and resultant is 19.62 HW whole square. This force will be acting, total force caused by wave is acting at 3 HW by 8 above the reservoir water level. Next is earthquake force. During the earthquake, the dam is starting moving, or the dam is started moving up and down left and right, back and fro. Due to this, there is a generation of the vertical acceleration and horizontal acceleration. The vertical acceleration can be determined as AV is equal to kV into G, where kV is the fraction of gravity. Generally, we are considering the value of the kVA ranging from 0.1 to 0.2, and acceleration due to gravity 9.81 or 10 as per consideration. Hence, the inertial force we can calculate easily F weight by G, that is the mass, and multiplied by this acceleration. F is equal to ma, Newton's second law. The net effective weight, then the weight of the dam minus inertial force into G. So F weight minus F weight by G into AV into G, and finally we are able to calculate FWT weight multiplied by 1 minus kV, where the value of the kV we are considering 0.1 to 0.2. Similarly, for horizontal case, there is horizontal acceleration AH, where this KH into G, where KH is fraction of gravity taking value of 0.1, and the net effective F weight in case of the horizontal acceleration is simply FWT into KH. Now question, sometimes people may ask, which situation is suitable for movement of the dam in case of horizontal and vertical acceleration. You can see here the downward vertical and toward the upstream horizontal. If it is downward, then inertia is going to oppose this to try to stabilize, and it is going to help. This upstream side is the best combination from stability point of view. What happens here when the dam structure is experiencing earthquake, means movement of up and down and left and right? So due to left and right, back and fro, this water is experiencing compression and expansion and come under dynamic state, and causing the dynamic force. You can see here, causing dynamic force. The dynamic force is no more triangular. This diagram I try to utilize. This is a parabolic in nature, and this parabolic in nature, you can calculate this area, and the resultant force of this parabolic acting toward the downstream at 4 by 3 h by pi. At this distance from this hill, the resultant hydrodynamic force is acting. As per Van Karman, the force hydrodynamic is simply 0.555 kh into unit weight of water into this depth of water present in reservoir. If we are going to determine the moment of the hydrodynamic force, then we are going to consider again multiplied by this zone, it become in cubic form. So we can simply say that 0.424 F hydrodynamic into this H, because we are going to involve this 4h by 3 pi. In this way we are going to calculate the force caused by hydrodynamic state of water on dam. Next type of force we are having here, concept of the impoundment of water. Impoundment of water due to flow of river. This flowing river is carrying some material which started depositing here in form of silt. The silt is under submerged condition, so it following the Raynick concept and require the calculation of the Raynick constant 1 minus sin phi or sin theta by 1 plus sin. This theta or phi is representing angle of internal friction. Internal friction of silt in submerged condition. Here in general condition, this the same as we are applying in case of water. So this triangular diagram here representing H silt, and simply it can be calculated. Force due to silt is half unit weight of the silt in submerged condition multiplied by height of silt deposit whole square multiplied by 1 minus sin theta by 1 plus sin theta. It can be easily calculated. Next type of force is ice force, and the dam side where the temperature change is below 0 degree following the freezing condition, then some surfacial part of the water is under freeze condition, and this going to affect the linear part length of the dam, because in downside it become smaller. As per concept, the volume of ice is generally higher than the water. Therefore, it results expansion thrust on the dam structure and going to push the dam downside. The general estimation about the thrust caused by this ice formation is ranging between 200 to 700 with average of 500 kilonewton per meter square. In engineering geological consideration for characterization of site, dam site, other aspect we have already discussed in elaborate form. Here I am happy to convey that S-shaped narrow valley having good to excellent rock mass quality is preferred for construction of dam. However, the poor and moderate type of rock in other type of valley requires lot of treatment and preparation and enhance the cost of dam project in view of future production. If we are going to see the different forces acting on dam going to affect the stability, then we are going to consider the weight of structure is going to support, where the horizontal force moving toward the downstream side going to disturb. Here the horizontal force in tailwater region going to support. Earthquake pressure is going to oppose, disturb the stability. However, the hydrodynamic force is also going to disturb. The shield pressure also going to push, but on the another side this is going to shield to minimize the build-up of the upthrust, that is very problematic for the stability of. So upthrust is a disturbing force Hydrodynamic is a disturbing force. Hydrostatic horizontal in headwater region, disturbing force. Wave force, disturbing force. Silt pressure, we are neglecting here to 0. Seismic force, disturbing force. Ice force, disturbing force. So except gravitational force, except this horizontal force acting in tailwater side and silt pressure, we are going to neglect. Other all forces are going to disturb the stability of dam. Friends, this concept I have developed with help of book written by Gangopadhyay, yes, on engineering geology and published by Oxford University Press. Then another book written by Well on engineering geology. Then another book for partial support, textbook of engineering geology written by Vatsavulu, and the Waltham T as foundation of engineering geology used for partial support. Friends, we have discussed in this class about various forces acting on dam due to impoundment of water, both static condition and dynamic condition, and other forces due to surrounding effect. Then the body forces due to structure. Weight of structure is responsible for the stability of dam, where the other forces in tailwater region and others going to support. Silt pressure is due to erosion, we are going to neglect because on another side is going to help. Hydrodynamic force is a major force affecting the stability of dam. Beside this, earthquake pressure, wave pressure and ice pressure is going to disturb the stability of dam. Geologically, S-shaped valley with good and excellent quality of ground is recommended for construction of dam in general. However, other area require lot of treatment and preparation and enhance the cost of project. Various kinds of forces expected to act on dam which cause instability to dam. Dear friends, in this class we have discussed about different forces acting on dam. Some of the forces is going to support the stability of dam, particularly the weight of structure. In addition to this, the horizontal force acting in tailwater region and vertical force acting in headwater and tailwater region is also going to support. Beside these forces, the majority of forces is going to disturb the stability of dam, particularly hydrostatic horizontal force, hydrostatic dynamic force. Hydrostatic dynamic force acting in any place is disturbing force. Then silt force, ice force, wave force, etc. However, the silt force we are going to neglect because the silt deposit is going to reduce the chances of filtration of water that responsible for upward acting force from the bottom of the dam. In case of this supporting horizontal hydrostatic force in tailwater region also not in consideration because the accumulation of water in tailwater region is representing more thrust working toward the earth in comparison to helping the stability of dam. So in this way we have discussed about different type of dams and the area suitable for construction of dam, and then different disturbing and supporting forces acting on them. Thank you very much.